Hi everyone, welcome to our final lecture of the course. Today what we're going to do is to tie everything up with what we'll call Dutch books. Let's see what these are. So remember that in last class we ended it by reviewing the Linda example. This was one of the examples in which people and human beings generally tend to systematically make mistakes about. And our tools of probability will show us how not to make mistakes. Now, just as a refresher, the example is that Linda is 25 years old. She just graduated college where she was part of many social justice clubs, even on the board of one. She partook in many demonstrations too. Is it more probable, the question is, that Linda is a bank teller or that she's a bank teller and active in the feminist movement? So by now you should really know that the correct answer is A, but people tend to pick B. Not everyone, but generally a majority of people. Now, one way to formalize this is that people might assign a lower probability to A and a higher probability to B. That's the mistake. So remember that B here is A and F, right? This was from the graph of last time. Now suppose that you assign a probability of 0.10 to A and a probability of 0.85 to B. Now remember also that one way to understand this is by operationalizing our beliefs as betting behavior. And so one way to understand what it means to assign 0.10 to A and 0.85 to the probability of B is that you'd bet 10 cents that Linda's a bank teller for every dollar you get back. And so what that means is that if I bet 10 cents that Linda is a bank teller, then if she's actually a bank teller, I'll get $1 back. And so I'll profit 90 cents, right? I buy a bet for 10 cents, so I lose 10 cents, and then I get $1 back. So $1 minus 10 cents is 90 cents. And otherwise, I just lose what I initially put in, which is the initial 10 cents. Now you would also accept a bet, right? You would think that this is a fair gamble, remember? The expected value under your lights is 0 of such a bet. And you'd bet 85 cents that Linda is a bank teller and a feminist. And now the problem that we left last class is that if you have these beliefs, you're now susceptible to a bet that you think is fair, but in which you're guaranteed to lose money no matter what the facts are. So that's a problem, right? If you do a bet and no matter what happens you lose money, then that seems to be senseless behavior, right? And just to make sure, this doesn't mean that you're going to take a bet in which you're less likely to win or not. What this means is that no matter what happens, you lose money. So it's impossible for you to win the bet. Let's see an example to make this concrete. Okay, let's start and construct this bet. So we still have the same probabilities of 0.10 for A and 0.85 for B. Then let's construct two bets that if you take them together, it will lead you to lose money no matter what. So you're going to, given your probabilities here, you'll take the bet because you think that they're fair. But if you take both bets together, what happens is you're going to lose money no matter what. It's going to be a sure loss. So let's construct this bet. The first bet is as follows. I can buy a fair bet by your standards from you that Linda is a bank teller. And what that means is I'll give you 10 cents, and that's the buying of the bet. And you pay me back $1 only if Linda is actually a bank teller. Now notice that you're going to find that this is a fair bet. If you run the expected values, and I urge you to do that, you are going to find this to be a fair bet, meaning that your expected value of this bet is 0. So now, what can happen? Well, there are 3 possible outcomes, right? Linda's either a bank teller or she's not. But if she is a bank teller, there's two conditions, right? She might be a bank teller and not a feminist, and a bank teller and a feminist. So we have three possible outcomes that can give us money back in this bet, right? Linda is a bank teller and a feminist. Linda is a bank teller but not a feminist. And Linda is not a bank teller. So let's see. Is there one of these cases where if you accept these two bets, you will be able to make money? Well, let's look at the first example. If Linda is a bank teller and a feminist, then you lose 90 cents from the first bet and you win 15 cents from the second bet. Let's see why. So what happens in the first bet if it actually happens that Linda's a bank teller and a feminist? Well, the first bet says that you pay me back $1 only if she's a bank teller. Now, she is a bank teller, so you do give me back the $1. But since I paid 10 cents for the bet, then it's $1 minus the 10 cents. So you lose 90 cents. What about the second bet? Here you win 15 cents because you pay me 85 cents and I give you back the dollar only if she's a bank teller and the feminist. And that happened. So in that case, you win the 15 cents. But taken together, these two bets, you can look up and do the math, you'll actually end up losing 75 cents. So if Linda is a bank teller and a feminist, you're not really in good shape because you lost 75 cents. If we look at the second bet, where Linda is a bank teller but not a feminist, well, here you lose 90 cents from the first bet and you lose 85 cents from the second bet. Again, let's go through these carefully. So the first condition still holds. She is a bank teller, and so you give me back the dollar from the first bet. Right? It says that you pay me back $1 only if she's a bank teller, and she is a bank teller, so you give me back the dollar. But since I gave you 10 cents for the bet, then it's $1 minus the 10 cents. What about the second bet? Can you get some money from the second bet? Well, if she's a bank teller and not a feminist, well, you don't get any money back because I said that I'll give you back $1 only if she's a bank teller and a feminist. But here she's a bank teller and not a feminist, so you lose the 85 cents. So here you're really in bad shape because you lose $1.75. Okay, so there's one more outcome, so let's see if in that outcome you're able to make some money. And that's a case where Linda is not a bank teller. Now what happens there? If Linda is not a bank teller, then you actually win the first bet and you win 10 cents, right? Because I give you 10 cents and you only give me the dollar back if she actually is a bank teller. And she's not a bank teller, so you get to keep the 10 cents. So you have that win. But what about the second bet? You paid me 85 cents and I give you back $1 only if she's a bank teller and a feminist. But if she's not a bank teller, then she's not a bank teller and a feminist. So you lose 85 cents from the second bet. And taken together, you also lose 75 cents. And those are all the possible outcomes. And so therefore, you're guaranteed to lose. You're really in a bad shape here, right? Because you bet one is fair by your standards. If you run the expected value, you'll actually think that the bet is fair, the first bet. You'll think that the second bet is fair. But if you take those together, then you're in a situation where no matter what happens, you're guaranteed to lose money. And that's kind of like a stupid bet, right, to take. If you take a bet where it's impossible for you to win, that's senseless behavior. Okay, so we've seen a situation where your beliefs violate the rules of probability and you're able to be put in what's called a Dutch book, which is a series of bets that guarantee you a sure loss. Now, let's introduce the notion of coherent betting rates. If your betting rates lead you to lose no matter what happens, then we say that they lead you to a sure loss. And this is what is called a Dutch book. A Dutch book is a series of bets that lead you to a sure loss. And we'll say that a set of betting rates is coherent if it's not susceptible to a sure loss. That's going to be our standard, right? It seems to be quite a minimal standard, right? A standard for coherent betting rates is that you is possible for you to win, right? Because if you get into a situation or a series of bets where no matter what happens you lose, that's senseless behavior, and we should call you incoherent. So a set of betting rates is coherent if it's not susceptible to a sure loss. And it's a mathematical fact, actually, that a set of betting rates is coherent if and only if it satisfies the rules of probability. And so we won't be able to prove this very rigorously in this class. I think it goes a little bit beyond what the tools that you have, but we'll show you an example of where if we violate one of the rules, then we are susceptible to such a bet. But also, if our betting rates are coherent if they only satisfy the rules of probability, then that means that our betting rates and therefore our beliefs should satisfy the rules of probability. Okay, let's go through one example where we violate the rule of additivity, and we'll see how we can put you into a Dutch book. So let's look at such an example. So a set of betting rates is coherent if and only if it satisfies the rules of probability. That's what we said. So let's get into the example. Let the following two propositions be. So H is that Harris wins the 2024 election, and T is that Trump wins the 2024 election. And let's also assume that the probability of H or T is equal to 1. Why can we do that? Well, because they're mutually exclusive, right? It can't be that both Harris and Trump win the election. Only one of them can win. And there are other third-party candidates, but let's, for the sake of this example and simplicity, kind of ignore that fact. These are the two candidates, and one of them is going to win, and you know that. Now suppose you believe that the probability of H is equal to 0.4, and the probability of T, namely that Trump wins, is equal to 0.4. So notice that if you add the probability of H and the probability of T, you'll get 0.8 and not 1. And so here you're violating the rules of probability. So this set of betting rates is incoherent, or these beliefs. Now let's see why, and let's construct a bet in which you're going to be in bad shape by the end of it. So suppose I propose to you the following bet, namely that I'll give you 40 cents and you pay me back $1 if Harris wins. Now you should accept that bet because you'll find that it's fair by your standards, right? You think that it's not that likely for Harris to win, right? It's less than 0.50% for her to win. And so I'll give you 40 cents, and if she wins, you give me $1 back. And you'll accept this bet given that you believe that the probability of H is 0.4. And similarly, if I say, well, I'll give you 40 cents and you pay me back $1 if Trump wins, well, here you'll also accept the bet because you'll deem it fair if you run the expected value of the game. But now let's look at what the possible outcomes are and how you're going to fare if either Harris wins or if Trump wins. So what happens if Harris wins? Well, if Harris wins, you lose 60 cents from the first bet and you win 40 cents from the second bet, right? Okay, so you lose 60 cents from the first bet. Why? Because I give you 40 cents and you pay me $1 back if Harris wins. And Harris actually won, so you give me the dollar back. So you lose $1, but you gain 40 cents from me buying the bet, so you lose 60 cents. From the second bet, you'll win 40 cents because I give you 40 cents and you give me back the dollar if Trump wins, but Trump didn't win, Harris did, so you get to keep those 40 cents. But here, you lose 60 cents from the first bet and you win 40 cents from the second bet, but then you end up losing 20 cents, right? So that's not great. So let's see if you can fare better if Trump wins. Well, if Trump wins, it's similar. You win 40 cents from the first bet, right? Because I give you 40 cents and you pay me the dollar back only if Harris wins, but she doesn't win, so you get to keep the 40 cents. But you lose 60 cents from the second bet because I gave you 40 cents in the second bet, but you gave me back $1, so that's 60 cents loss on your part. And in both cases, you lose 20 cents. So you're, again, in a bad situation, that no matter what happens in the election, you lose money. And note that if you only accept one of these bets individually without the other, then you won't be in this senseless behavior. You could either win money or lose money. But the important thing is that you'll deem both of these bets fair, so you'll be able to take both of these bets, and in both cases, if taken together, you're going to lose money. So now I think we have enough tools to present the Dutch book arguments. And these are arguments to give local justifications for why your beliefs should cohere with probability. The argument goes as follows. Beliefs that license senseless behavior are irrational. That's one of the premises. And that makes sense, right? If your beliefs allows you to do senseless behavior, then this behavior, or these beliefs that allow you to do them, you want to call these irrational beliefs. The second premise is that beliefs that violate the rules of probability lead to senseless behavior. And this is what we've seen, right? Beliefs that violate the rules of probability, right, when beliefs are operationalized as betting behavior, they do actually lead you to do senseless behavior. And the senseless behavior here is what? It's that it allows you to get into a Dutch book. The senseless behavior is that you'll accept bets that will guarantee you a sure loss. And that's not very good, that's senseless behavior. And from these two premises, and it's in the second premise that we've done most of the work that in the past few weeks we've been leading up to, which is that beliefs that violate the rules of probability lead to senseless behavior. So it's a mathematical fact that if your beliefs don't cohere with probability and your beliefs are operationalized as betting behaviors, then you'll always be susceptible to a Dutch book. And so we want to say we have at least a minimal condition for rational beliefs, which is that they should follow the rules of probability. And this allows us to answer Hume. Remember that Hume says that we can't rationally justify a system of inductive logic, or induction. But what we've done here is given local justifications for why to update our beliefs with probability theory, right? When you come to a decision problem where you want to think carefully and think, what's the rational thing to do here? A wise thing to do is to write down your beliefs as probabilities and see if they cohere. And if they don't, then you know, or at least you have some reason to believe, that you're having irrational beliefs. So, sadly, we're coming to the end of our class. But now we have enough tools to look from a bird's eye view to what we've done so far and what we've learned. So, the course started by introducing you to deductive and inductive arguments. Remember that deductive arguments are those in which the conclusion is supposed to be guaranteed from the premises, whereas in inductive arguments, the conclusion is not supposed to be guaranteed from the premises. But there are good and bad inductive arguments, and we wanted a way to formalize and allow us to make better inductive arguments. Why do we care about that? Well, because most of our lives we're making inductive arguments, not deductive arguments. Right? Science works that way. Most of the arguments you make in everyday life are going to be inductive arguments. So having a tool to make better inductive arguments should make you better reasoners. We then looked at some paradoxes of induction. Remember, we looked at Hume's problem of induction, where Hume gives a pretty convincing argument for why we can't rationally justify our inductive practices, or that we can't rationally justify any particular scientific inductive logic, right, on a global scale. But what we're going to do, or what we did in this class, is to say, okay, we'll accept Hume's argument, but we're going to kind of sidestep it. Because we're going to say we don't need a global justification for induction or a particular scientific inductive logic. What we're going to do is give a more local justification. And to do that, we started to introduce you to some cognitive biases in reasoning. We went over the gambler's fallacy, we went over the disjunctive and conjunctive fallacies, and we went over the base rate neglect fallacy. Now, knowing that we make these mistakes in reasoning isn't all that useful if we don't know how to overcome these mistakes or these shortcomings. And this is what we did in the last part of the course. We introduced you to probability theory, right? That should be useful independent of all the philosophical arguments. But having this probability theory in hand, we've given you some reasons to think that your beliefs should, in many cases, cohere with probability theory. And we've also went over some interesting philosophical questions on the interpretations of probability. Now, this was a short summer course, so we couldn't get into all that much detail, but there's a lot more to explore. And on that note, I'm going to thank you for being with me in this class. I hope you enjoyed it. I enjoyed teaching it. And I hope this introduces you to inductive logic.